This is like the second of our master's workshop series in the topic of longitudinal data analysis. I think I don't know how many of you might have attended the previous one. I think maybe some similar time last year. I gave the first of the series, which is focused on generalized estimating equations, or GEE. And in this one, I'll focus more on random effects or mixed effects models. And so hopefully sometime next year we'll have like the third one in the series, which is kind of more intensively recorded longitudinal data. So today I think I'll just as you can see from the title, we will really look at longitudinal data, and in particular the approach of random effects or mixed effects models. Let me try to. Um, and so I would assume that the audience would have knowledge in basic regressions for independent data, for example, linear regression for continuous data, logistic regression for binary data, or Poisson regression for const data. So they are all what we generally call generalized linear models in the statistical literature. And in the models you are more familiar with, they probably like typically you use it in settings where you have independent samples. But in this workshop, we'll try to see how do we extend those models to correlate the data in longitudinal studies. And I will also assume there's some familiarity with matrix algebra that I'll be showing some formulas, like not very complicated ones, but there will be some formulas to help understand the models. So here's the outline. So at the beginning, I'll try to give a brief introduction about longitudinal data and what are the features about longitudinal data that we must take into consideration when constructing statistical models. As then the second part will be more focused on, focus on continuous data. In particular, we'll use linear mixed effects models, or LMM. And then the third part will be more for maybe continuous but non-Gaussian data, but all discrete data like binary or const data. So we'll talk about generalized linear mixed models, which is really the extension of the standard generalized linear model, but adding additional random effects. So and will end with some discussion. So I think I'll get started. So for both linear mixed effects model and the generalized mixed effects models, like a few aspects to understand. Oh, actually, any maybe statistical models is kind of a like you want to know what type of data are those model most suitable for. And then you wanted to sort of also understand what the model means, how the model are specified, how different model components can be interpreted. And then also about how do you estimate your parameters in the model, typically in terms of regression parameters like odds ratios or hazard ratios. And then finally, how do we do inference? Once you got this point estimate, how do you get standard errors? How do you get 95% confidence intervals and p-values? So let's start with longitudinal data. I assume that most of you are somewhat familiar with this, so hopefully we can go through this section relatively quickly. In longitudinal studies, subjects are often measured repeatedly over time. You can have this type of data in clinical trials, for example. You recruit people, and then you get some measurements from baseline, and then after some time period, maybe there was some intervention or some medications, and then maybe let's see after the end of the trial, you measure the outcome again, and you wanted to compare the outcome before and after the intervention. So everybody really have two time points, right? In some clinical trials, you maybe measure the outcome sort of more densely. Maybe let's see, 1 month, 2 months, up until 1 year. So in that case, you have more than two repeated measures per subject. And then also in general, maybe more observational studies or cohort studies, you could also think about, you could also measure outcome repeatedly, like growth curves. You have some subjects, you measure their height or weight over time, as then you wanted to see how the trajectory look like and the patterns in the variations in trajectories. Now in longitudinal data, because you have repeated measures, so as compared to like a typical cross-sectional study where you have everything only at one time point, now you can actually investigate different questions. You can not only investigate differences in the subject's baseline levels, which you can already done this in cross-sectional study, but in longitudinal one, because you have repeated measures, you can also investigate changes over time as a make inference about the patterns in changes. So why longitudinal data analysis require special statistical methods? Why not just use your standard regression? I think the most obvious reason is that you have the same subject has a few repeated measures. Those measures tend to be correlated with each other. So we'll go back to this repeatedly throughout this short course, and so you will see like where the correlation could come from, what are the possible correlation structures, and how do we deal with these different correlation structures in the models, and also showing examples how big these correlations could be. So this is oh, and by the way, I think I may have skipped this one. So I just also want to say that a lot of the materials is including the data examples and this area is very well developed in the statistical literature. So I took a lot of materials from the existing two textbooks. One is from Deagle, Hagerty, Leon, Ziegler, 2002. It's called Analysis of Longitudinal Data, published by Oxford. And the second one is called Applied Longitudinal Analysis by Fitzmaurice, Laird, and Ware. So this is published in 2004. So like most of the data examples are from these two books. They are publicly available. Okay, so this is like the first example. This is like looking at the CD4 counts over time for I think maybe around 1,000 to 2,000 subjects. It's from the again from the Deagle et al. Book. So we sort of for longitudinal data because you have multiple for time points for each subject. So naturally you just connect the lines so you can show the trajectories, right? So as you can see, for most people, the CD4 counts goes down over time, but you also see a lot of variability, right? Some people tend to be, have higher CD4 overall at any time point. Some people tend to have lower CD4s. And then in terms of visualization, when you try to connect like 1,000 curves, it gets a little bit busy. So it's another way to visualize this is you can using plot the points, but only select a subset of subject to connect the dots. I think this has become a little bit easier for you to see the trajectories. This is another example. It's a growth curve for guinea pigs, I believe. Again, from the Deagle et al. Book. It's showing the weight trajectories for those pigs across 9 weeks. Again, we connect the lines for each individual, so you can see that. So generally speaking, the weights increase over time, as in there are some pigs which tend to have higher weights, at all time points. Some of them tend to have lower. Some of them maybe start a little bit high and drop a little bit lower. So you see all different kind of trajectories. Now from this pattern, I think in particular like this one, you can clearly see that because it's a pattern where some subjects they tend to be have higher values across all time points. So if you just run like a standard regression, look at the residuals. The residual for this person tend to be positive all the time. So clearly they are correlated, right? So this actually in longitudinal study, so this so-called, we call this within subject correlation. It's the main source of difficulty to deal with. So let's just give an example. Let's see that you have three subjects, A, B, and C. Each of them, we measure them at three different visits, visit 1, 2, and 3. So we use the notation Yij to indicate the J's measurements for the ith individual. So the first one really have three measurements, Y11, Y12, Y13, and the second one, has also have three. So I think it's reasonable to assume that different individuals are independent, meaning any measurement for A is independent of any measurement in B because they're different individuals, right? But for the same individual, those three measurements, they are likely correlated because they share some underlying characteristics for this person. And then because this correlation is not zero, it's mainly the part that we need to take care of in statistical models. Now I think let's just look at how the correlations are represented. Let's maybe first revisit in linear regression. In linear regression, so the models we typically assume your observed data is signal plus noise. Signal where we try to use a bunch of predictors to predict the outcome. So you can have models, basically a linear combination of some predictors, and the coefficients beta j's they tell us how strongly each predictor is correlated with the outcome, right? So this part is the signal part, and this is the noise part. For the noise, we typically assume they are independent with each other and they follow some common distributions. And then we can do least square, we can get estimates for the beta coefficients, we can estimate standard errors, p-values, and etc. And I think one of the key assumptions here is that the errors have to be independent with each other. Otherwise, typically your standard errors will be wrong. Your p-values and 95% of confidence interval will be wrong. And then as we mentioned before, in the longitudinal setting, these independent assumptions actually are violated. So that's why it's not a good idea to simply ignore the correlation and use this standard linear regression. Now, so that also let's see, try to write this into more like a vector or matrix form. So let's say if you have a linear regression, your outcome is yi. In this case, in the longitudinal case, in this case, I think let's assume you have three subjects, right? So if you write the outcome y, it will be a vector of 3. And then the error epsilon is also have a vector of 3. And we assume that the errors are independent, which means that if you look at the covariance matrix for this error, so it should be 0 in off diagonal, meaning the error for subject 1, subject 2 are 0, so they are independent. So you got this variance covariance matrix, which is like diagonal matrix. It's actually the diagonal are the variance, the off diagonal are all zeros. Now if you go to a longitudinal data, things are a little bit different. Let's see, we again use Yij to see the J's measurement for the ith subject. So for each subject, you have 3 measurements. And if we look at their variance covariance matrix, so the diagonal are still the variance, so it's non-zero. But the off diagonal, now they are also non-zero because there are some correlation between them. If we see the correlation are denoted by rho, so in this case, so the variance covariance matrix is no longer a diagonal matrix. It's have some general structure that have additional parameters, though, indicating how strong is the within subject correlation. So writing in matrix form for this one single subject, so the error variance would be, sigma square times like a correlation a correlation matrix here, like have this type of structure. So that was just for one subject. If we write it down for like, let's say if you have three different subjects, now how would the variance correlation matrix look like? Now what we know is that between different subjects, they are independent, right? So that means this block is really the covariance matrix within the first subject. Now this block is the covariance matrix between subject 1 and subject 2. So this part is all 0. This is between subject 1 and 3 is also 0. This is between 2 and 3 also 0. So like all of those off-diagonal blocks are 0 because of the independence among subjects. But within each subject, within subject 1, we know that it's not diagonal because there's within subject correlation here, right? Within subject 2, similar story. For subject 3, similarly. So if you look again, so now you look at the whole variance covariance matrix for all three subjects, you will see that the overall structure is that you have this block diagonal, within the diagonal blocks, they are not they have some correlations, but in these off diagonal blocks, they are all 0. So this is kind of the structure to keep in mind. So this is just a really similar correlation matrix, but writing it in like more like a block format. Okay, so so here I think so I'm trying to go through the last few slides just to give you an idea of how the difference between like longitudinal and independent data. So I think the key thing to keep in mind is like for each subject, when you have independent data, you really have very simple like covariance structure. So basically independence. But then for longitudinal data, then because the correlation, now you have to sort of take into account these correlations. So now in terms of statistical model, so again, in regular regression, you regress the outcome y with a bunch of covariate xij and beta as your coefficients. These are the residuals, right? If you ignore the correlation, you assume that the residuals are independent. But in longitudinal analysis, we wanted to explicitly account for this correlation. So the model would assume that the residuals, they are not independent anymore. They have some sort of structure. So we wanted to use statistical models to understand and account for those structure. Now this is trying to tell you the next slide is trying to tell you. So what if you ignore the correlation? You know the model is not this model is not correct, right? But you still use it anyway. So what could go wrong? I think I'll go into more details later, but just to give you the conclusion, what could go wrong is you could have invalid, means wrong inference, meaning that if you fail to account for the correlation, so standard errors are wrong. Because if the standard errors are wrong, the competent intervals are also wrong, the p-values are also wrong. So you will get wrong conclusions, and you could also in some cases you could also get the correct conclusion, but do not use the data efficiently. What I mean by that is if you look at the regression coefficients, for continuous data, actually you are getting the wrong target, but you are not using the data efficiently, meaning you actually throw away some information from the data. So so the sort of the visual representation of these two different mistakes. The first one, when you are getting incorrect or wrong inference, that means actually you are shooting the wrong target. Let's see that your target is here, like if you but you are trying to shooting around this area. So you're totally getting the wrong scientific conclusions. The inefficient use of data meaning is that you are actually getting the right target, right? In the left-hand side and the right-hand side, you have two different estimation methods, basically, or two different models. This first one, so even though you're not shooting like exactly as a target, but like there's some errors each time, right? If you took the average of those, they're kind of close to the middle, meaning so overall you're shooting the right target, but like not very precise. So there's a lot of error. On the right-hand side, you're getting not only shooting the right target, but also you have greater precision, right? So that means you are using the data more efficiently. So yeah, so to summarize, it's really kind of important to that when you have longitudinal data, please do not just ignore them and do your standard regression. It's really important to you try to use specialized techniques for longitudinal data. I think that's basically the first part, which is really trying to give you like a brief introduction of longitudinal data. So I don't know. I guess I want to take a pause here to see are there any questions for this part?
There weren't any in the chat, but if anyone wants to speak up, if you break for questions, Chongzhi, that seems reasonable.
Yeah. So if anybody have questions, please feel free to send a message in the chat. You can also unmute yourself. I'll just give a brief pause here. Okay, I didn't hear any questions, so let's keep going to the next part, which is really focused on linear mixed effects models for continuous data. So again, so we have the outcome Yij. We wanted to do a regression model between Y and X, and we know that the error has some sort of a structure, right? So now I think again in the previous workshop we talked about generalized estimating equations, which is saying that let's try to specify some structure in the correlations, giving like a working correlation structure. Let's see working independence or exchangeable or autoregressive correlation structure, and then let's try to estimate the model parameters. The mixed effects model, the random effects models, is kind of working from another angle. It's trying to see, let's try to think of some underlying mechanism of what could have caused this correlation between them. And then can we use statistical models to account for these correlations? So the basic idea is, again, this is like more obvious from this growth curve example, is that you notice that there are some of those peaks, they just tend to have higher weight overall, right? So the idea would be maybe individuals have their subject specific trajectory over time. Or another way to think that is each subject have their own characteristics that might have been correlated with the outcome at each time point. So let's try to maybe in the statistical models, let's try to use something to account for those characteristics. So that's why we want to introduce so-called random effects. So again, in this example with the three subjects, right? Let's see that there's some underlying characteristics of the first subjects. It's U1. It's actually is correlated with the measurement at each of the three visits, right? Of course, at each visit, there will be also visit-specific deviations or random noise. In this case, I'm denoting as like E11 with the noise as the first visit for the first subject, and E12 is like the second visit. So basically, this is saying that the U1 is unobservable. And then for the second subject, you have unobserved random effects U2 and U3 for the third subject, right? So what we are seeing is that at each time point, what you actually observe is a combination of two things. One thing is like the underlying individual characteristic, but not observable. A second thing is like some random variation or noise. And putting that into statistical terms, the two models we use the most are so-called random intercept and random slope models. So I'll start with this random intercept model. So this model is saying that let's say that your outcome is y, your covariate in this case is time, is Tij. It's basically the time for the GS visit. Okay, so you observe that, let's say you wanted to use a linear trajectory to model the growth curve. But you notice that different individuals, they tend to have, a different, some are generally a bit higher, some are a little bit lower. So meaning if you look at the lines, if you use line to represent each curve, you notice that their intercept is different, meaning their level at the baseline is different. So so you introduce a random intercept UI to the model. And then you can regroup this very easily to the UI can be grouped with the intercept. Now what this is saying that you are saying that for each individual I, right, it's still a linear growth curve, and then the slope of the growth curve beta 1 is the same across all individuals, but the intercept for the ith individual is pretty specific. It's beta 0 plus UI. So the intercept for subject I and J are very different. Now if you introduce this sort of additional UIs, and we know that the UIs are not observable, so we treat them as a random effects. So we assume them they all come from a common distribution with mean 0 and with some variance. And then the epsilon in this case will be just a random error. So we assume it has follow a Gaussian distribution with mean 0 and some variance. We also want to assume that the epsilon ij is an error, and then the random effects are independent. That's kind of for identifiability reasons. So this is like the random intercept model. Again, it's if you look at the visual representation, so it's really seeing that in the population average, this is the population average growth curve. But we notice that each individual, their curve, they have their specific curve. For individual A, this person has the same slope with this population curve, but it has a little bit higher. So it's highest a higher number in intercept. So individual B again has the same slope, but has like a lower intercept. Now I also wanted to point out that what type of correlation structure this type of a random intercept model will induce. So to investigate that, we just need to do some like easy, simple matrix algebra. We just try to calculate the covariance between Yij and Yik. So basically the two measurements, the measurement at visit J and visit K, calculate their covariance. Now because these betas, they are like really fixed values, so they don't really affect the covariance. So this is equivalent to seeing the covariance of UI plus epsilon ij and UI plus epsilon ik. And you try to expand this into 4 different terms, and notice that the first term becomes basically the covariance of UI and itself. It's really seeing that the covariance between the random effects and itself, right? So it's really the variance, it's not 0. But once you look at all the other terms, the covariance between the random effects and the error, we know they are 0 by our assumption. This is also 0. This is covariance of error at different visits. They are also 0 because the residual errors, they are totally random. So once you do the calculation, you realize that you want the covariance between any different visits, J and K, they are exactly the same, and they equal to the variance of these random effects. And then if you want to calculate the variance of Yij, they actually are a little bit larger. So it's the sum of the variance of random effects and the sum of the residual error variance. So because of this, now we write out the variance convergence matrix for a same subject. It's the same if a subject has 3 visits, right? So their diagonal term are the variance, sigma square, which is really sigma u square plus sigma e square. But the off diagonal, the covariance are always sigma u square, right? And if we also try to separate this into a variance time a correlation matrix, you will see that in the correlation matrix, the diagonal are ones, and the off diagonals have this number, which is the proportion of sigma u out of sigma square. So in this case, this would be our correlation. As you notice that this correlation is exactly the same between variable 2 and 3, between variable 1 and 2, 1 and 3, and 2 and 3. So that means that from the random intersect model, it actually implies a so-called exchangeable correlation structure. Exchangeable meaning it doesn't matter which two visits you take, they always have the same correlation. And in fact, you can calculate exactly how large this correlation is. It is called intra-cluster correlation coefficient, or ICC. So it can be calculated basically by sigma u squared divided by the total variance sigma square. Again, the total variance is really the sum of the sigma u square and sigma e square, right? So yeah, so this is about the random intercept model. So both from the graphs and also from the mathematical formula. So you can see that this model is saying that we allow different individuals to have the same slope, but different starting point. But because the slope are constant, so the implications are the variances will be constant over time, meaning that you don't sorry. So if you see the variation, like the difference distance between A and B at the beginning and at the end, they are roughly the same. And also we also just see that the correlations are exchangeable, right? So this is like the model assumptions. In some cases, it might be reasonable. In some cases, it might not be. So so what in some if you think that this is too restrictive, you might want to consider more flexible models. A easier one would be you can add a random slope. So this will be the second example. If you have a linear mixed model with random intercept and random slope. So in this case, again, you have this kind of a population average linear trajectory, beta 0 plus beta 1t, but then you allow each individual to have a different intercept. So you add a random intercept at UI0. Oops. And also you add another slope for this individual UI1 Tij. So this is so adding allow the slope to change as well. And if you do a simple regroup of this equation, you can see that for the ith individual, the subject specific intercept is actually beta 0 plus ui0. The subject specific slope is beta 1 plus ui1, right? So you really allow both intercept and slope to be vary across individuals. And again, the assumptions we typically assume both random intercept and random slope follow a Gaussian distribution with different variance, and you typically allow them to have to be correlated as well. And the epsilon is an error. Error is kind of independent with all the random effects. Now the visual representation of what this model means is here. So let's see, this line again is the population average growth curve. So it has, it has some intercept and slope, and but in this model we allow each individual A, we allow it to have a higher starting point, meaning the intercept is higher. But also you can see it grow a little bit faster, right? It's more steep. So we allow the slope also to be a little bit larger. For individual B, it starts lower, so the intercept is negative, random intercept is negative, but also the slope is also smaller. Now because of you have both random intercept and random slope, so if you again try to calculate what are the implications for the correlation structure, if you calculate the covariance matrix between Yij and Yik, I will not show the details, but if you do the matrix algebra, you'll find that it depends on the variance of a random intercept, the variance of a random slope, but also the covariance of random intercept and slope, and it also involves the time for the j's and the k's visit. No, what this tells us is that this correlation structure is no longer exchangeable, right? Because it varies based on the time t, ij, and tik's. So the correlation structure actually is not allowed to change over time. So that's why this is a little bit more flexible than the random intercept model. But then on the other hand, the model, we also have more parameters to estimate in the sense that you have additional parameters for the variance for the random slope, the covariance between random intercept and random slope. So the model becomes a little bit more complicated as well. So by now, so we sort of briefly reviewed two special cases of a linear mixed effects model, a random intercept, a random slope model. So I think I'll just quickly check if there's questions about it.
Yeah, we have one question, Dr. D. It says, what would be the advantages of using the generalized mixed model approach versus the GEE? Apologies if you talked about this in previous talks. That comes from Wendy.
Yeah. Thank you, Wendy, for the question. Yeah, it's a great question. I think I will leave more detailed answer to the end because towards the end I'll do have like one slide talking about the differences between these models. But I'll just say something quickly for continuous outcome data. Like if you're doing a linear regression for Gaussian data for continuous outcomes, if you're using GE versus linear mixed effects models, you can often get very similar results. In particular, the point estimates for your regression coefficients are typically very similar or sometimes even identical. Of course, that depends on, what correlation did you use in GE, what working correlation did you use in GE, and what random effects structure you use in the random effects model. But they should be very similar. But I think that one of the main difference is that GE you're only getting population average effect. So if I ask you to maybe make inference or predictions on a specific individual, you cannot get that from GE. But with random effects model, you potentially can, because you allow each individual have a subject specific curve, right? So we have those random effects UIs, and I'll talk about later that you can estimate those random effects. So once you estimate them, then you can construct a subject-specific prediction curve. So I think that's kind of the advantage of the mixed effects model in this case. But on the other hand, GE is said to be more robust in the sense that even if you specify the wrong correlation structure, your standard errors are still correct. This does not hold in linear mixed effects models, meaning if your true model has both random intercept and random slope, if you only use random intercept in your model, the standard errors could be wrong. Yeah. So this is kind of like a very brief answer for now. Yeah. Okay, so next part, I would just say, describe some, more generally, not just the random intercept, the random slope model, but more generally, how a linear mixed effects model for longitudinal data look like. So the general model formulation has a form where you have the outcome Y, you have covariance, Xij, and Zij. So Xij are so-called the fixed effects covariance. So they influence the model through a regression parameter beta. Beta are fixed parameters, meaning they are fixed values, they are not random. But a different set of covariates, Zij, they influence the outcome in a different ways because they influence them through random effects UI. UI are subject-specific random effects. It can be a scalar or it can be a vector, meaning more than one random effect. In that case, we assume the UI come from a multivariate normal distribution, and you have the residual epsilon ij. So and X ij and Zij, they can be, you know, any covariates or subset of covariates, including time. And they can also be like you know, in the case of a random intercept, actually Zij is just a constant, it's just like a ones. And you know, so basically again the model have this three different parts: fixed effects, random effects, and noise. So what do each part do? Let me see. So the role of each part is somewhat different. So the fixed effects are mainly affects the mean trajectories of your outcome, meaning, you know, we assume that the UIs have mean zeros, absolutely have mean zero, right? If you take the mean of this whole response, those two parts all have mean zeros. So the mean function, the mean curve, is mainly depending, it decided on the fixed effects. But if you look at the covariance structure, when you look at the covariance structure, you know, these are fixed values. They do not, they can drop out, right? So the covariance is really decided by these two terms. So if you look at the covariance between two different visits, J and K, you know, it's totally decided by the variance covariance matrix of the random effects and also the design matrix of the random effects. And if you look at the really the variance, mean or the covariance of the J's visit and itself, and you, so I'm sorry, there's a typo here. This should be the covariance of Yij and Yij. In this case, it depends not only on the random component, but also on the residual error variance. But overall, you can see that. So really, the fixed effect decides the mean structure. The random effect decides the covariance structure. So this is very important to keep in mind. As the model have three sets of parameters, you have a regression parameter beta from the fixed effects part. You have the variance covariance matrix for the random effects, and you have the error variance. As in terms of how to estimate this model, this is very well established. I will not go into the details, but just say that, you know, typically we use some versions of maximum likelihood estimates. So it meaning that, you know, we try to look at, you know, given a set of parameters, you can write out the likelihood function, which is a probability of observing the data, given the underlying distributions, right? And then you try to maximize this likelihood, trying to find the parameter values that maximize this function. So that will sort of give you, you can get a point estimate for all your parameters. And there's like a statistical theory, which also allow you to get standard errors for all those parameters. And once you have those estimates, the UIs are the random effects, right? So they are still really meaningful because whether UI is higher or lower, it indicates it's really helpful for you to sort of reconstruct the growth curve for the ith individual. So we can also estimate those random effects by a method called best linear unbounded prediction. Again, I will not go into the details, but your you know, typical statistical package, they would implement all those estimation methods for the coefficients, for the standard errors, and also they will also give you the estimate of random effects. Now in terms of inference, by inference I mean really mean like confidence intervals or hypothesis testing and p-values. So I just wanted to point it out one thing, which is for the regression coefficient beta, they are actually pretty straightforward. You know, for most packages, they give you standard errors, p-values. You can trust them, no problem. But for the covariance matrix, for the random effects, they are actually a difficult scientific statistical problem, because the standard statistical theory do not apply in these cases. The reason was being that if you think about a variance of a random intercept, for example, right? So the parameter has to be non-negative. You cannot have a negative variance, right? So because of those restrictions, a standard theory do not work. And hypothesis testing, confidence bands actually are pretty challenging. So at least a few references, those are statistical, very statistical papers tell you, oh, in different cases, how do you get the p-values? So I guess the overall a message I want to convey is that in some of the packages, they might give you like a p-value for testing random intercept or testing random slope, for example. So I would recommend you try to be a little bit more careful and then look at which method they use to calculate the p-value. If they are doing some sort of a chi-square type of test, most likely the p-values are not valid. If you are using something like Bootstrap, I think I probably believe those p-values more. Yeah. And finally, so the linear mixed effects models, because we are using likelihood methods to do the estimation and inference, so we can automatically account for missing at random. Yeah. So I think so yeah, in terms of comparison with GEE, so I think I just briefly answered this earlier. So again, this is for the context of continuous outcome data where you use linear mixed effects models. So just to reiterate the differences, the GE is really more focused on so-called marginal effects or population average effect. So you are really kind of compare differences, population average effects. For example, you are comparing, let's see, two different treatment groups, right? You are saying that, oh, on average, does treatment B has a stronger effect than treatment A, right? But in linear mixed effects model or random effects models, we are typically more focused on subject-specific interpretations. Actually, I probably should go back to the model here. Now, the reason why the coefficient beta has subject-specific interpretation is because if you look at the model, so whenever we try to interpret some regression coefficient, right? So remember, let's see if you have more than one covariate, we see that the coefficient for covariate x1 is, the average change in the outcome y per unit change in covariate x1, but also holding everything else constant, right? If you have more than one covariate, so you have to always see that you are holding all the x2, x3 to xp, holding everything else constant. You only change x1. What will be the effect on the outcome? In the linear mixed effects model, if you look at this, so you notice that what you are holding constant are not only the covariates, but also has random effects as well. So if you are holding UI constant, but UI is subject specific, so that means what you are actually doing is within subject comparison. It seems that the average change in the outcome per unit change in the covariate for the same individual. You cannot, if you compare across individuals, the difference will not be beta. It's because, the reason is that, again, like, I'm sorry, so like for different individuals, they have different intercept. So like, I think probably I should go back to this curve to, yeah, see, it's more easier to explain. Yeah, right. So so in the linear mixed effects model, remember, right? So the average population average curve yeah, this is the population average curve. This is the curve for A and B. Notice that they have different intercept, they have different slope, right? So so I think so when we are comparing effects, so we are for if we are sort of comparing yeah, if we hold some, let's see if we look at the change between time 0 and time 1, right? So the for subject A, actually the effect is actually like from here to here, right? So it's kind of like you have see more steep changes. For subject B, it's from here to here, like the slope is a little bit lower. But in this model, we allow different individuals to have different curves. But if you take the average, it will be this curve from this curve like here. Yeah. And then the second difference between GE and linear mixed effects model is that they account for within subject correlation in different ways. So GE, it really is a marginal model. You try to specify what's the correlation structure likely, like exchangeable, like autoregressive. But linear mixed effects models, you just explicitly assume existence of some random effects, and that random effect is causing the correlations. And different options of random effects implies a different correlation structures. And finally, I think we just mentioned that the linear mixed effect model allow more subject-specific inference and prediction. I think this is like for all the this is like for the methods part for the linear mixed effects models. I would next, I think I'll leave the generalized mixed effects models to the second half. But I do want to spend some time going through an example. So if you hopefully kind of give you a more intuitive idea of how to use linear mixed effects models in practice. So I think I'll probably try to go through half of this example before we take a break. And then so you're welcome to also play with the data during the breaks. So the first example is from a phase 2 randomized trial comparing two drugs to reduce schizophrenia symptoms. And it is like a pretty standard pre-post design with a sample of schizophrenic patients. And so you have measure everybody as baseline, which is a pre-intervention. And then you have post-intervention, you measure the outcome repeatedly at different time points. In this case, at week 1, 2, 4, 6, and 8. So 8 weeks is like the end of the trial, and the outcome is a so-called positive and negative syndrome scale. It's or we call it a PANSS score. For this score, lower is better. Higher is worse. And this is how the if you plot the data, so there are two different groups basically corresponding to different drugs. So you will see if you just simply plot the data by the treatment groups, here's what you get. And then again, we know each the left-hand side is the treatment, the first treatment, and you see the trajectories. You see that in generally speaking, for most individuals, the PANSS score actually become lower over time, meaning the drug actually is helpful for reducing the symptoms. But you do see variations across individuals. This individual, for example, starts lower and also gets even lower. This individual starts higher, also gets lower. But there are also exceptions, like this individual, the score actually gets lower after first week, but then somehow it increases in the following weeks. And then on the right-hand side is we're showing the trajectories for the second treatment group. Now, again, generally speaking, you still see the sort of the score decrease over time. Again, meaning the treatment is working. But it seems to show somewhat sort of different trajectories. Like if you look at the slope, especially during initial stages, it seems to be decline faster than the first treatment, right? And then you also see like variations across individuals. Like some individual, like this individual, you see like very fast declines of the score. But there are some individual like this one, you see that it's actually it remains pretty constant in the beginning, but it actually increase in the end. So I guess the overall, and in each of the subfigures, I also plotted the average score at each time point in this blue line in the left and the red line in the right. So to give you an idea of sort of the average trajectories. Now on the second page, I'm showing you really like the trajectories by individuals. I think it's basically you get this really you have the same message as this figure, but we plotted for each individual. So for you, it's hopefully it's easier to see some of the patterns. And then the first 25 subjects I plotted in black. So those are from group A, and from 26 to 52. So they are plotted in blue. So they are the from subjects from the second group. Again, you see, so overall, you see that for most people, it's generally speaking, the score decrease over time in both treatment arms. But also you see a lot of variability, right? There's some exceptions, like some people actually, the score actually increase over time. And for some individuals, the decline may be like more, closer to linear decline. For some of them, you see more like, decline and then maybe plateaus or at some point. Yeah, so there's a lot of variations in terms of individual specific trajectories. So then how can we use linear mixed effects model to analyze this data? So this is like the procedure. I think I want to really emphasize that I think I have seen many people like when they got the data like longitudinal data, they just did not spend a lot of time trying to explore or understand data and then just try to fit the model directly. And then you fit the linear mixed effects model, you get your coefficients, and then you interpret the coefficients, and you're done with the analysis. I think that's something I really wanted to warn against. I don't think it's a good idea because every model typically have some assumptions. And I think it's really important to spend a lot of time before fitting the model and also after fitting the model, in the sense that before fitting the model, you wanted to make sure you spend a lot of time understand the data and explore the data. Look at the distributions of the data, look at, any sort of missing data patterns or outlier patterns. And also for longitudinal data in particular, you wanted to plot the data and then got an idea of what the trajectory will look like. Do they look like more like linear trajectory, or do they look like some sort of nonlinear pattern, or change points, or quadratic pattern, or as in so that's, and also you wanted to spend some time explore the correlation structure in the data. Do you see evidence of within subject correlation? How strong are the correlations? Are the correlation structure, do they look like exchangeable, or do they look like the correlation changes over time? Because those are all informative in terms of what models you want to fit, what type of model you want to fit for the mean structure, what type of model you want to fit for the random effects structure. And then so after fitting the model, and I also recommend doing more model checking. Like every model typically have some assumptions. Do these assumptions seems reasonable? Do you see clear indications of maybe some assumptions are violated? If so, do you need to revise your model to account for those data features? So I guess so overall, what I'm saying is please don't just take the data, fit the model, and be done. That's really if you do it that way, it's very easy to use the wrong model and get the wrong conclusions. Please spend a lot of time before fitting the model and after fitting the model. So go back to the to this data. So I think we have seen how the data look like, right? So the first, for longitudinal data, so it's always like, you have the mean structure, you have the covariance structure. So we always start with the mean structure. So let's see what type of a trajectory or structure we should use for the mean structure. Now this data is actually a so-called balanced design, in the sense that everybody really, they have they have measurements at the same sort of a schedule, right? They have time 0, which is baseline, and week 1, 2, 4, 6, and 8, right? So it's really the same for everybody. So, a easier way is to just calculate the mean, right? Calculate the mean for each treatment group at each time point, and you got the trajectory. This is like for this halo treatment, you got this blue line. You have generally decline, but maybe seems to be decline a little bit faster at the beginning. And then for the red line, it's again it's a decline, but seems to decline a little bit faster um, at the beginning. And then so we can think about what models we want to use to model this two kind of trajectories, right? So the easiest model is we assume like a linear relationship. We put a week variable, that is the time in weeks. Assume that there's a linear relationship between, so the outcome is a linear function of the week, but also there's a treatment effect. We assume that, for two different treatment groups, they could have different intercept, right? The first treatment has intercept beta 0 and slope beta 1. The second treatment has intercept beta 2 and slope beta 3. Here, beta 3 is the interaction in the slope. And in this case, actually, this is the one we are most interested in. The reason being that, this beta 2 tells us is really, if you let week equals 0, right? So this term disappears, this term disappears. So really seeing that beta 2 tells us the difference in the PANSS score between two treatment groups at baseline, right? So it's really, so that beta 2 parameter telling you, the difference in between baseline. But if you're because it's from the randomized trial, if you did the randomization correctly, so this difference should be pretty small. So any difference you observe should be purely due to chance. So that's why it's not our main interest. But the main interest is more like, how fast or slow the decline over time, right? So it's like the rate of decline. So in terms of models, meaning the interaction term, so beta 3 is our primary parameter of interest. So this is like the linear model. And then some of you, if you look at the figure, you might notice, oh, linear model, it's probably not very bad, but it's kind of, you appear to see that the effects, the slope were kind of pretty steep in the beginning and some would plateaus maybe after 4 weeks, right? So if you observe this, if you want a model to reflect this type of trend, you could, have a plateau model. In this case, you would define this variable, which is saying if it's before, let's see, in this case, we consider 4 weeks as a change of slope. So let's see, before 4 weeks, this variable is exactly the same as a week, but after 4 weeks, I'll fix this at 4. So that was that, and then you put this time, transform the time into your model. Now what this does is saying that you are seeing that the effect is always, you allow some change before week 4, but after week 4, it should stay constant. And then of course, sometimes you might think that maybe a little bit too strong. You're not exactly sure if it's really constant after week 4, right? You could also consider a so-called change point model. The change point model is saying you allow a change at some point. In this case, if you see that's you allow a change at week 4. So what you would have, you put the week variable in the model, but you put another change point variable. This change point variable is 0 before week 4, but it's the same as week after week 4. So what this does is to allow you to see. I think I'll show you an example later. You understand it a little bit better. So it's sort of allow you to using two parameters to see that we allow the slope to have some slope at the beginning, and then allow the slope to change at a later stage. And again, so you could have interaction of this change point variable with the treatment. So let's try like this model and see how they fit the data. So this this is from the first linear model, right? The linear model, assuming a linear trend. So not surprisingly, the blue solid lines, these are some observed average trajectories over time. The dashed lines are model fitted lines. This model is a linear. It's really trying to find the best line that is closest to your observed trajectory, right? So you can see that for this group, it's not that bad. But for the group two, I'm sorry. For group two, somehow so you can see that you see a little bit more difference, right? It still captures the overall trend, but seems not to acknowledge sort of the change in slope. Now, this is what you get if you fit a plateau model. The plateau model in this case sort of assume a change point at week 4. So for this first group is kind of fitting a line like here, then force the line to be constant after week 4. And then for the second group, so you can see again allow a decline after week 4 and assume a constant after week 4. Right? So again, this is not perfect, but if you sort of compare this to the linear line, so you see overall speaking, these fitted lines are a little bit closer to the observed trajectories, right? And then this one is like a change point model. And for this example, I think I played with different change point. I found that maybe change point at week 2 works a little bit better than week 4. But anyway, so just to give you an example. So if you this case allow the model to have the line to have a slope at the initial stage. But then after week 4, we allow the slope to change, but we're not forcing the slope to be 0. So it could be any number, positive or negative. So you can see, compare this to the previous one. Now you have this part is forced to be constant, right? But in the change point model, you allow a negative slope. For the group 2, similar story. So you're kind of assuming a different slope at the beginning of the ending stages. And then of course, you could also have a so-called saturated model in this case, because the time points are really, we have, baseline week 1, 2, 4, 8, 6, or 8. If you really want it to be flexible, you can sort of create a lot of dummy variables, right? So you allow the effects from baseline. So for beta 1, beta 2, beta 3, beta 4, beta 5, you have these 5 parameters to describe the change in trajectory. And similarly, for the treatment, for the second treatment group, you also need additional 5 parameters to describe the change at each week, right? So the model become much more complicated. You have many more parameters, but it is indeed a little bit more flexible. So what this model will do is actually, if you fit the model and plot the fitted curve, it's overlap exactly with your observed means, which is also not surprising because it's the model really seeing that you allow the slope to change at each time point. So it's really coincides with your observed data. Okay, so this is like the sort of the exploration of the mean model. I guess the message I want to convey is that we always say that all models are wrong, but some are useful. A statistical model typically always make some simplistic assumptions, so that based on these assumptions, you can make some inference. You can extract some features from the data. But those assumptions, some are reasonable, some are plausible, some are maybe not for a particular data set. So I think that's why it's important not to sort of after you have the data, not just choose a pre-specified model, just fix the model and be done. I think it's really important to try different models and then see how well they fit the data, and then help you decide which means structure you want to use. In this case, typically the best model is not the most flexible. Typically, it's the one that's makes the best compromise between simplicity in the interpretation and also flexibility or model fitting. So in this case, I think I would probably not choose a saturated model, even though it provides great fit, right? Because if you wanted to summarize what is the treatment effect, you have really like 5 parameters, and then it's not easy to to interpret this, and then and also sometimes this you could have collinearity problem if you put too many covariates in the model, right? And on the other hand, I mean, linear regression in this case actually is not too bad. I would say, especially if you go to individual plots, for most of individual, linear actually are not too bad. So I would say that it's okay if you wanted to sort of accept that, it's giving you a rough trend. The good thing is it's giving you one parameter, right? So if you wanted to do, getting a little bit more detail in the pattern, sort of capturing a little bit more refined patterns, you could go with the plateau model or the change point model. I guess there's no single best answer to this, but I do hope that, what you would do when fitting a model is to explore different options and go through this process, explore different options before you decide which one to use. And then I also say something quickly about the correlation, then we can take a break, I think. So so as we mentioned that in longitudinal data, correlations are really the key part that you have to account for, right? So we know that generally there should be some within subject correlations, but for your particular data set, how strong is the correlation? What does the correlation structure look like? Does it look like exchangeable, or does it look like maybe they change over time, right? So this is something we can also explore before fitting the data. So the way to calculate the correlation, so once you have a good mean model, so you would calculate fit like a mean model. For example, you could use any of the previous mean model that we just explored, and then you calculate the residuals, which is calculated by taking the difference between observed and the predicted score for each individual. And then at different time points, you can plot the pairwise scatter plot to give you some idea, right? If you look at most of these plots, you see clear evidence of a positive correlation, right? Maybe they tend to be a little bit stronger, maybe along here, meaning if the time is really close, they tend to be stronger. Whereas if you go to this area, the correlation appear to be weaker, right? And then you can also calculate the covariance matrix between those residuals. So I'm showing the matrix here. Again, the diagonals really, are ones because the correlation with itself, right? So the off diagonal, if you look at here, it's really correlation between baseline and week 1. This is like week 1, week 2, week 2 and week 4, right, etc. So you see that generally along this line, the correlations are higher. The smallest here is about 0.44. The highest it could be as high as 0.85. So really very high within subject correlation. Now, if you go towards this corner, generally speaking, the correlation become weaker, right? Over here, it's got to somewhere around 0.29. So I guess the take-home message is, are there any sort of evidence of within subject correlation? Yes, that's a very, very strong evidence of within subject correlation, right? So that means especially ignoring the correlation is not acceptable. But also like how is the correlation structure look like exchangeable? I think if you look at this number, you probably will see maybe exchangeable does not seem like a very good approximation of the true correlation structure. Yeah, it seems like the correlation would change over time. Yeah. So I think this is like the about half of this example. So I think let's just stop here and take a 10-minute break. Let's continue at around 10:30. So what I will do very soon, I'll also, for this is like data example, I'll also send in the chat the link to download the R codes and also the data set. So if any of you are interested, you're welcome to play with the data before we continue with model fitting. Yeah.
We also have a question in the chat. Do you want to address that once we're back from the break, or do you want to do that now?
Yeah, that's a good question. I think I'll choose I'll answer this question when we come back. Yeah.
Okay, sounds good.
Okay. Hi everyone. Let me see. So I think let's restart. So in the first half we just mainly let me just I think start. Okay, yeah. In the first half we just mainly go through linear mixed effects models, and we kind of halfway through this example, data analysis example. I think I saw some questions. I'll probably try to go to the try to answer the question first. So that's a question saying
Do you want
okay,
me to read them for you, or are you able to see?
I'm able to see on my side. So I see a question, could you provide insights on the assumptions to be considered when building this type of model? So I think I'm not sure, please, if you can, please be a little bit more specific. Like, are you talking about the general linear mixed effects models? Are you talking about the model we are considering for this particular example? Yeah. If you
I think, yeah, hi. I'm kind of curious about both. So I think like just in general, like if it would be helpful to understand like the a priori assumptions that need to be made to do a general linear mixed effect model, and then it I may be misunderstanding here, but it seems like you're using the same data. From what I could understand, you're using the same data set and exploring different model fits. So is that something you can do? Like, could you explain how you choose which model? For instance, the ones you've been going over, saturated, change point, plateau.
Mhm.
So how do you eventually choose which model you want to use with your data set? Yeah.
Yeah, that's good. That's a great question. So I think in terms of model assumptions, I think so the linear mixed effects model really, as we went through, it really have two parts, right? The fixed effects and the random effects. So they play different roles in sort of the assumptions. The fixed effects part really determines the mean structure, meaning like the trajectories or dependence with covariates. So which covariates should enter the model and in what form, right? Should be in linear form or in like in some sort of change point form or in quadratic form. So as in the random effects really decides what type of covariance structure the model implies, right? The random intercept model would imply an exchangeable model. Random slope would allow sort of the covariance structure to vary over time, right? So I think so those are really kind of the main assumptions. So when you are actually analyzing a particular data set, so that's kind of why, that's why I kind of assume I would recommend you try to play with different model setups in the sense that we just explore the mean model, right? Mean model we give examples where you could consider like a linear relationship or plateau shape or change point shape or even the so-called saturated model, right? So I think I think definitely you can do that. But I think that's all really encouraged because let's see if you don't you look at the data at all, maybe you just simply assume a linear shape, then what if the true relationship was nonlinear, right? You're not really able to kind of capture that trend. So that's why I think you explore the data and then the sort of that give you some idea of what candidate model to look at. That's really important and recommended. And in terms of choosing different models, I think I just mentioned it very briefly. So it's always like a trade-off. So that's really no single best answer to see, even in these data examples. I will not tell you that, for example, like linear model is the best or change point model is the best, because the saturated model is the best. I think so because each time you kind of have to a lot of time you have to think, all the models are approximations. So I think you wanted to choose so-called acceptable models, meaning the assumptions are plausible. Not doesn't have to be perfect, right? So let's say if you for the linear model, it's even though it's probably not the most does not give you the detailed trend, but it does actually capture the overall direction, right? The decline in the score, right? And it give you just one single parameter to tell you basically the rate of a decline, right? So if you you look at the residual plot, and if you look at the fitted versus observed plot, if you feel like that type of approximation is acceptable and you are willing to to sort of compromise that with the convenience you get in getting like a single parameter to estimate the coefficients, then it could be work well for your case. But then if you look at that residual plot and you feel like, oh, okay, I don't think that's reasonable, that's good enough. I wanted to sort of capture the more patterns sort of in the change in slope. Right? In that case, you probably will have to go to the want to go to the plateau or the change point models. But then the compromise you make is that you're not going to have one single parameter. You will have to use two parameters, right? To tell you the change in the slope in the initial stage and in the second stage, right? Or the change in the slopes. So yeah, I think so overall, I guess there's really no single best answer, but like if you see clear and also there are some statistical tests that you can do to help you guide as well. For example, you could go to the change point model and test if the coefficient for the changing slope is that significant or not. That can also be a guideline as well. Yeah. So hopefully that answers the question. I think it's really like I don't in the model building for basically all statistical model. I don't really think there's like fixed set of rules or thresholds that you should use. Oh, in this case, like if the p-value is smaller than 1, you should like use this model versus that. I don't think so. There's like a strict guideline like that. It's more a lot of times more of an art. But I do wanted to emphasize it's really important that you check the model fitting and then you plot the data. You kind of get an idea of if the model is clearly nonlinear, and if you choose a linear model, that's where you could make a lot of mistakes. I think
That's
there's an
helpful. Yeah, thank you.
yeah, sure. Yeah. So another question is going back to random effects. Okay, so the next question is about deciding what variable to add as a random effect or not. And saying people do all sorts of goodness of fit tests. I saw people do likelihood ratio tests, which I don't agree with. Or when subject field knowledge is limited. Okay, yeah, it looks like this question is more about how do you select variable to include for random effects, right? So again, see if you goes back to that's why I think it's important to sort of understand the rules of the random effects. So random effects are really their primary role is to help us account for within subject correlations, right? So what the different structure you choose, random intercept or random slope, or even adding additional variables, the implications are they kind of allow different correlation structure, right? If you only have random slope, again, you only allow exchangeable correlation. If you add a random slope, you would allow this correlation to change over time. But if you don't have additional covariates, you are saying that for any subpopulation, let's see, older people or younger people, or male or female, right? So it's different subpopulation. You all allow different subpopulations or people in different treatment groups. You assume that the correlation structure is the same among different subpopulations. But when there's either scientific knowledge or empirical evidence that you found that for example, in this case, I plot the correlation right here. If we plot the correlation matrix among the two different treatment groups, if you see they have clearly different correlation structure, that is like a clear indication that you probably should put the treatment also as a random effect. You know what I mean? I think it's really like, the sources of so it's typically from, if you have scientific knowledge indicating that the correlation structure could depending on some covariates, it would be a good idea to put them in the model. If you don't have prior scientific knowledge And then, you know, from the exploratory analysis, if you start to explore, you found some differences, some factors you think that, you know, if you stratify by that factor, you see differences in correlation structure. That's also a good indication to put them in the model. In terms of testing, to decide which random component to choose, I don't necessarily think that's a bad idea, but I do think that it can be misused a lot because, as I mentioned earlier, so the p-values when it comes to testing the random effects variance are really tricky. So like a lot of existing statistical packages, even though they might give you a p-value or even give you like a p-value from a likelihood ratio test, I do not necessarily trust all of those p-values because they are really complicated issues. So I know some packages, they are just using simple chi-square type of test to give you a p-value, but those are definitely wrong. So they should use like more sophisticated methods, but I'm not confident that all packages are using the correct methods. So that's why, you know, I'm not a big fan of relying heavily on p-values when choosing random effects. Yeah. Okay, I think I saw one more question, which is we recently got a suggestion for one of our analysis to add a covariate as both a random and fixed effects. The covariate is currently only a random intercept, but the suggestion was to add it as a fixed effect. Does it make sense? It seemed weird to me. Well, it's another good question. I think again, it's to answer this question again, it goes back to the roles they are playing. You know, if a covariate, there's nothing wrong with having some covariate as both a fixed effect and a random effects, as long as you think the role, you understand their roles. If you add them as a fixed effect, you are really seeing that this covariate, you know, is a really important factor for the mean model, meaning it could be a really important predictor by itself, or it could be an important confounder or effect modifier, right? If you believe that a variable plays any of these roles for the mean response model, yeah, sure, please put them in the model. And then for a covariate, you know, if you put them in the random effect, you are seeing that this variable is important because it affects the within subject correlation structure. So meaning that a simple way to check that is that, you know, if you stratify on this variable, you might see different correlation structures, right? So yeah, so I think so I guess, you know, I don't think there's anything wrong with adding some variable in both fixed and random effects because the roles they are playing are kind of different in both parts. Yeah. So let's go back to this data example. I think I think let me see if I'm having a little bit trouble. I'm sorry. I think I have a little bit trouble going between my slide. Okay, yeah, okay. So in the previous slides, I showed you exploratory data analysis with both you know, to show you an example of how do you explore different mean models, how do you explore the correlation structure, and now let's try to fit some really linear mixed effects models. So I'm starting with a naive model where you know, as we mentioned before, you know, the linear effects, it does not provide the best fit. But as an illustrative example, I'm actually showing the linear mixed effects model, assuming the linear effects. Because I think, you know, it's really easy to interpret, but in the R code, I did provide it, you know, if you prefer like a plateau model or change point model, you can also see the R code of fitting mixed effects models with these different mean structures. So for ease of presentation, I'm choosing linear effects here. So again, so linear effects is kind of trying to fit a line to these observed trajectories, which is not perfect, but still kind of capture the overall trend, the decline in the scores, right? So if we fit a linear regression model, meaning let's just only have fixed effects, no random effects. That also means that you sort of ignore the correlation, right? We said it's not acceptable, but still, I'm still showing the model anyway. So if you fit the model, we put the treatment indicator, put the time in weeks, and also put the interaction between treatment and time in the model. So these are the estimated coefficients you would get. So again, the treatment variable, this variable is not our primary interest because it tells you the difference in treatment at baseline, right? If randomization is working well, it should be small. In this case, it's not small, but it's not significant. And the time really tells you the decline, the rate of decline among the reference group, which is treatment A. So you see a statistically significant decline of 1.5 unit per week. And then the interaction term, this is really what we are mostly interested in. It tells you the difference in rate of decline between those two treatment groups, right? The coefficient is estimated to be negative 0.4, and it's not statistically significant from this linear models. Now, what if we add random effects? This case, I just add a random intercept, right? So, and then I'm using LME function in R. It gives you estimate of a coefficient. So first, let's look at the fixed effects. So you notice that, for the, if you, again, I focus on the interaction term, the point estimate is still negative 0.4. Still similar as before, still not statistically significant. But you do notice that the standard error is a little bit different. So here is 0.5. In the previous slide, it's about 0.7. So it's smaller here. And if you look at the random effects, the main parameter is the variance of the random effects of standard deviation. In this case, it's estimated to be 14, about 14, and the residual error standard deviation about 12. What this could have indicated to us is we can calculate the so-called intra-cluster correlation, right? So there was a formula before, but in this case, you can do that easily. So it means this model basically tells us the within subject correlation is about 0.58. So it's kind of medium level of a within subject correlation. And then we know that this model assumes an exchangeable correlation structure, right? So, from the exploration, we know that that's kind of maybe not the most plausible. So because we do see evidence of the correlation change over time, so we tried adding a random slope. So we have both random intercept and random slope to the model. First look at the regression coefficients. The regression coefficients, so the treatment and time, so the coefficient is still about negative 0.4. But the standard error is again a little bit different from the random intercept model. Still not statistically significant. And if you look at the random effects part, because we have two random effects, so we have the standard deviation for the random intercept, we have the standard deviation for the random slope. We also have the correlation between the two random effects. So you actually have two additional parameters to estimate in this model. So now let's look at model fitting. You fit three different models, right? So what are the implications? How do you decide, how well they fit the data? So the first model is from the fixed effects model only, meaning the simple linear regression, right? So what this model is assuming that for each treatment group, there's like the same trajectory, the same decline, the same intercept, the same slope, basically the same line for each treatment group, for each group A and group B. When you look at the, I'm plotted the observed versus the fitted values. So you can see that, for some trajectories, like this one, for example, this one, or this one, they're actually not that bad, right? It captures the decline and the slope and the intercept appear to be reasonable. For the second group, this one, the fitness is not that bad. But then you also see examples where fitness is really bad, like here, for example. It consistently kind of underestimated. I think the reason was you assume everybody have the same trajectory, but of course this person has always higher score at all time points, right? This person, the slope is kind of different. So you see many examples where the fitness is not that good. So meaning that you assume a common trajectory for everybody is not necessarily a good idea. So let's look at the random intercept model. Now this model improves over a simple linear model in the sense that it allows everybody to have a different intercept, but it still assumes the slope to be the same. So, for a lot of trajectories, you are certainly better than the previous one, right? But because you force the slope to be the same across individuals, it still provides, very perfect for some people, like this one, for example. This one, it forces the slope to be negative, but actually this person's score is kind of a constant, maybe slightly increasing, like this one, right, as well. And then, so what about the next model, which is both random intercept and the slope? Now you can see the goodness of fit improved across pretty much everybody, especially on these two ones, where you know that the individual slope was maybe like constant or even slightly increased. But previous random intercept model do not allow that. But this this random slope model allows the individual. So if you look at the goodness of fit, clearly this model with both random intercept and random slope works the best. And by the way, I think this is probably kind of another way to help answer the previous question of how do you choose between different models. I didn't show like p-values of testing among those models. Again, because I don't necessarily recommend that, but I do recommend using empirical evidence in terms of if you plot the fitted versus observed trajectories. Actually, you can see very clearly that some models are just fit the data better than others. You can also, I did not show it here, but what you can also do is try to calculate the model estimated correlation matrix and compare that with empirical correlation matrix. It's another way to check if you have sufficient random effects. Now let's go back to the to summarize this analysis. Look at the model coefficients. So I put the three models: fixed effects only, and the random intercept and slope together. So you can see if you look at this parameter, the interaction is what we are most interested in. So the parameter estimate is negative 0.41 across all three models. So that's kind of again try to reflect the fact that even if you ignore correlation or even you use the wrong random effects, you actually get correct estimate for your parameters for continuous data. But what you do notice is that the standard errors are different, right? 0.77, 0.5, and 0.71. So the difference was resulting from their different assumptions in the correlation structure. So unfortunately, unlike GE, in GE, while you specify different working correlations, and we know that as long as you use robust standard errors, you are going to get the correct inference, even if you specify the wrong correlations, right? But in random effects model, you don't have that robustness, meaning this standard error is correct only if there's no random effects. So this standard error is correct only if the random intercept is correct model, only if there's no true random slope. So this standard error is correct if there's random intercept and slope. Okay, so that's why in order to get correct inference, so it makes it's kind of more important that you try to get the right models for the random effects part. So that's why sort of the exploration we did earlier, empirical explorations to find out what structure makes the sense, and also doing sort of the model checking diagnostics, fitted versus observed. Those kind of really helpful to help make sure that you choose this model. And then, so finally, my one might be interested in the pre-post treatment effects, right? In this case, the post this time is in the scale of weeks, when the end of the trial is 8 weeks. So if you are really saying that between the end of the trial and the baseline, it's 8 weeks. So the effect is 8 times this interaction variable. So the estimated effect is about negative 3.3. But again, and it's not statistically significant. So if we were to summarize this analysis, also I didn't focus on this, but from here you can see that these coefficients, the decline over time among the reference group is actually statistically significant. So we do see that there's a 1.51 unit decrease in the score it should be per week, and a decrease about 12 units in about 8 weeks in the first treatment group. And in terms of the treatment effects, we see the evidence that we see that there's maybe some difference, but it's not statistically significant. And I think I do wanted to emphasize to everyone here, because I assume most of the audience is not statisticians. So I see this misinterpreted a lot. So if you are testing a statistical hypothesis, if you reject the null, right, you will see there's evidence for the association between some factors and other factors, right? But if you do not reject the null, if the p-value is greater than 0.5, I often see people, interpret that as they are not associated, but that's not correct. So the correct interpretation is that there's not sufficient evidence to suggest association. It's not the same as no association. I mean, the truth signal, there may be an association, there may not be association. It's just that in this particular experiment, based on the data we have, we don't have sufficient evidence, okay? So, but if you were to conduct another experiment to collect more data, maybe you will find out there is association. So I guess it's really important to distinguish between no association versus no not sufficient evidence. Yeah. So finally, the 3 models, they give you similar estimates for the regression coefficients, but unfortunately, they give you different standard errors. And as I mentioned, you lose robustness in the random effects models. So it's kind of important to think more carefully and explore a little bit more before you decide which random effects makes the most sense. Okay, so I think this is for the example. So that's the end for the basically for linear mixed effects model. So we have probably a little bit over 30 minutes to go over the generalized linear mixed effects model. So I'll go back in slides. I think for some reason I can only do this page by page. Okay, so let's go to spend some time on generalized linear mixed effects models, and hopefully also go through an example for binary data to show how to use those models in practice. So for generalized linear mixed effects models for non-Gaussian data, so it could be continuous data, but non-Gaussian. It could also be discrete data, like binary data, like const data. So before before we introduce the longitudinal data, we first review briefly for independent data. For continuous outcome, a linear regression, we would typically build a model on the average of the outcome as a linear predictor of some covariates, right? So you have coefficients beta, which tells you really the effect of the covariate on the change in the outcome. For binary data, now why it's a binary, it can only take values between 0 and 1. So we'll typically work with the probability of the yi equals 1, which actually is also the for the binary data. I think you probably also know that the probability of y equals 1 is also the expectation or the average value of the random variable. So typically we use a logit link. So we have the expectation, we take the logit link, and it can be interpreted as the log odds for the outcome y equals 1. So we use a regression model of xi beta on this log odds of the outcome. For the cons data, like Poisson regression, so typically we assume the takes the logarithm of the average values and then regress on some linear some covariates. So they kind of all have kind of similar forms in the sense that it's all the left hand side is always some sort of a transformation of the average of the outcome. The right hand side is always like a linear predictor on the covariates, right? So in the statistical literature, we call this type of models generalized linear models. So we use G to represent whatever transformation that's suitable for the particular type of outcome, and we link this to the linear predictor of covariates. And then for this, all the linear regression, logistic regression, and Poisson regression, they are all special cases for the generalized linear models. And the estimation and inference, we can use the same framework, especially through iterative weighted least square to estimate all the coefficients and estimate standard errors and p-values and etc. Now, this is for the independent data. So how do we handle longitudinally measured non-Gaussian data? I mean, as you can guess, from the linear mixed effects model, we basically add random effects to account for within subject correlations, right? So for the general non-Gaussian data, we can do similar thing to the GLM, meaning previously, you only have you link the average of the outcome to some fixed effects, but now to account for the correlation, you just add a bunch of random effects, right? So in the most general form, so we assume there's a random effects UI. It comes from a multivariate Gaussian distribution with mean 0 and some covariance matrix. Again, special examples could be you can only have one random effect, random intercept. You could have random intercept and random slope. You could also include some of the covariate Xij into the random effects as well. So the roles these fixed effects and the random effects are playing is really similar to what they did in linear mixed effects models, in the sense that the fixed effects really decides the mean response, and the random effect decides the covariance structure with like really the within subject correlation structure. Let's just give an example. Let's consider a random intercept model for binary data, right? So your outcome is like you wanted to model the log odds of you get Yij, the J's response for the subject I equals 1. We want to model the log odds, and then so you're going to use for the fixed effects part, let's see, just the linear effects, beta 0 plus beta 1 times t. But then in order to allow within subject correlation, you add a random effect UI, random intercept UI. You assume this UI come from a Gaussian distribution with some variance. So again, similar to the continuous data case, if you have this random intercept, you can calculate that the correlation within subject correlation structure is become exchangeable, meaning if you look at the correlation at visit 1 versus visit 2, or visit 1 versus visit 3, or 2 versus 3, you're always going to get the same correlations. And also, I'm sorry. And another thing I want to point out is still like when you are interpreting the coefficient beta 1, just remember that when we interpret the coefficient, we need to hold everything constant, right? So in this case, we have to hold the UI constant. So but UI, is a random effect. It changes from individual to individual. So the only way to keep UI constant is you are only comparing any individual to himself or herself, right? So it's really saying that the beta interpretation of beta 1 is a log odds ratio for a positive response in the outcome for 1 unit increase in the time Tij. And then you are getting these effects, conditional for each individual, like not really average across individuals. Yeah. So yeah, this is just giving like a special case to emphasize this point. So let's see, we still consider this binary data pre-post design, where Tij, the time is binary, still the same model as this slide, beta 0 plus beta 1 T plus UI, but now T is either 0 or 1. 0 means baseline, 1 means after the trial, post intervention. So you can see write a few special cases for individual I. Just write out the log odds. When for at baseline, it's simply beta 0 plus UI, right? Because when T is 0, the slope term disappear, and then at time 1, it becomes beta 0 plus beta 2 plus UI, right? Because beta 1 is really the change from baseline to follow up. And for individual J, you can write out similarly. At baseline, the log odds is really beta 0 plus UJ. At post intervention, it's beta 0 plus beta 1 plus UJ, right? So you can look at a few changes. Let's see, first, if we only focus on subject I want to calculate the pre-post change in the log odds for the response for only subject I. So you are really taking the difference between this and this, right? If you take the difference, the intercept canceled out, the UI canceled out, so you are left with beta 1. Similarly, if you are focused on look at the different subject J, calculate the pre-post changes. If you take the difference, again, still beta 1. So this really tells you that no matter which individual you look at, if you are comparing the pre-post change, you always get the same effect, which is a slow beta 1, right? But if you were to look at the difference, let's see, between the log odds for subject I pre-intervention and for subject J at the post intervention, meaning for J you are looking at the post intervention, so it's beta 0 plus beta 1 plus UJ. But for pre-intervention, if you look at subject I, you have a beta 0 plus UI. If you take this difference, you notice that the intercept canceled out, but the U and UJ generally they are different. So actually this difference is generally different from beta 1 from your slope. So I guess this is really like a simple exercise. I want to go through it to emphasize to you that for the comparison, for when you're interpreting the slope, it's really important that you kind of focus on this subject specific, because the comparison for any subject is a slope. But if you are doing comparison cross individuals, it's generally different. It's not the slope anymore. So just say a few words more generally about the GLMM in general. So I think I showed examples of some general methods considerations. Hopefully go through this very quickly. So you have this generalized linear mixed effects models, fixed effects, and the random effects. The random effects have these distributions, right? So the parameter in the model are this regression coefficient beta, and also those variance covariance matrix for the random effects. So those are the two main model parameters. And in terms of how to estimate, actually it's actually not that easy. It's somewhat challenging. So in the statistical literature, I think in the past 20 years, there have been different methods of estimation for the model. Generally speaking, people wanted to still do some sort of maximum likelihood, but because it involves random effects, so we have to sort of average over the distribution of the unobservable random effects. This process is much easier for the continuous data, but for the generally non-Gaussian data or discrete data, it become really tricky. So generally, there are a few statistical packages they implement this through maximum likelihood with numerical integration. There are some variations of the methods implemented in different packages. And similar as linear mixed effects model, once you estimate those parameters, what you can also do is do some sort of a subject-specific prediction or inference, meaning you can also estimate the random effects UIs. And based on that, you can sort of calculate more subject-specific, trajectories. So in terms of the software, so there in R a few packages like NLME, LME4, and I also should also list for the GLMM. There's a package I often use called GLMML, which yeah, and then for SAS, like those are kind of two common procedures. Yeah. So yeah, I think that's kind of most about the general methods for GLMM. So for the rest of the time, I hope to go to another data example to illustrate how do we actually analyze data from a real example. Okay. Yeah, so this example is again from another randomized trial. So the data and example is from the second book is called Applied Longitudinal Analysis. So it's basically a randomized trial comparing 2 hour treatment, A and B, for toenail infection. So the outcome is, I'm sorry, it keeps messing up. The outcome is a binary example, is the presence of some condition. Has but I think they coded the outcome as having no symptoms or minor symptoms, and maybe more severe symptoms as 1. So the time it was measured at week 0, which is baseline, but also at follow-up times, including week 4, 8, 12, 24, 36, 48. Yeah, it's roughly 12 months for most people. And I do wanted to notice that the in this trial, the data was like a little bit irregular in the sense that previously, so everybody kind of follow a really exactly the same schedule, right? Week 0, week 1, week 2. In this case, I think those are the rough time points, but for each individual, it may be not exactly 4, maybe like 3 or 5 or something. So that everybody's schedule can be a little bit different. So here's how the data would look like. Okay, the data is like can be done publicly available from the website of the book. So it has a few variables. There's a subject ID in the first column. Second column is the binary response. And then the third column is a treatment variables. 0 and 1 indicate 2 different medications. And then there's a month, time in months. The last column is a visit. They coded as a visit 1 to 7. And you can see that the time here is not exactly as round numbers, right? It could be this, I think month 0.84 is kind of like slightly less than the first month. Yeah. Yeah, so everybody, so the time for the first subject is a little bit different from the second subject. Yeah. So first, I think as with continuous data, it's really important to sort of also explore the data and understand. For the binary data, because it's about the proportions, right? So if the data were like more regular, I would recommend, creating some tables. You just estimate the proportion of zeros at different time points, maybe for different treatment groups or something. But because the time is irregular in this case, it's really hard to try to group them into tables. So what I try to do is to using smoothing to add smooth the proportions of positive outcomes over time between two treatment groups. So roughly speaking, you can think about the smoothing is a little bit like, you can think about, for example, around baseline, right? So you choose a window around baseline, you put like all the data around baseline and estimate the average proportions. And then you let this window to move slightly over time from baseline all the way to the end of the follow-up. So you get sort of the average, roughly speaking, the average proportions of positive response over time. So for both treatment, you can see that it appears, so 0 is here, there's probability of 0. So you can see that at the beginning, they tend to have like probability of roughly closer to 40% of reporting a positive response. As then the probability decline over time, and maybe around here, it kind of goes really small. Yeah. And also I do wanted to say that some of you, when you look at here, you might think about what are the implications for building the mean model, right? Does that mean that we might want to prefer like a plateau, some type of plateau model or change point model? Actually, not necessarily here. The reason is because in continuous outcome data, we just look at the response directly. The link function, we do not do any transformation, right? But when we work with probabilities, we typically do a logit transformation. So in the probability scale, you see this kind of a plateau or change point effects. But if you plot this in log odds scale, you actually don't necessarily see the change in slope. So I just want to mention this. So this is kind of like give you, and also if you maybe try to understand what's kind of do you see any difference in the treatment effects? It's not, sorry, it's not very obvious, but you can probably tell that, let's say maybe around 5 months mark. At 5 months, so the left-hand side, the probability here maybe like around 0.15, but here it's really closer to 0.1, maybe 0.112 or something. So you do see on the right-hand side, it seems like you have a stronger effect, and also towards the end, this tend to maybe go up a little bit. But on the right-hand side, treatment B, you generally see lower score and they tend to stay more constant towards the end. So there appears to be a stronger effect for treatment B, but let's see, use statistical models to confirm. And then another thing is like similar to the continuous outcome data, we can also look at what is the covariance within subject correlation structure, right? So each subject you have 7 different visits, even though the time do not line up perfectly as an approximation, I can still sort of generate this correlation matrix. I just really group all the ones together, even though maybe some are like 3.5 months or some 4.5 months, but I think they are close enough. So as a rough estimation, so I calculate this variance covariance matrix. So you can see this from this matrix. First of all, there does seem to be a pretty strong evidence of within subject correlation, right? A lot of the numbers, 0.7, 0.8, towards here is closer to maybe 0.2, 0.3. So overall, there appears to be kind of pretty strong evidence of within subject correlation. And some people might ask, for binary data, the correlation coefficients might not be the best metric to capture the association, right? So you might prefer something like odds ratio. So I also showed within subject odds ratios comparing different visits. And in fact, I'm actually showing the logarithm of the odds ratio in this matrix. So in the log odds ratio scale, 0 means really no association. positive numbers means strong positive association. So you can see actually there you see very strong, again, very strong within subject association, right? You see like over here, these numbers are like maybe 4s and 5s. Remember they are in the log odds ratio scale. If you go back to the odds ratio scale, those correspond to the odds ratio of like 280, super strong association here. And even the smallest number here, like 0.97, if you transform that into odds ratio scale, it's an odds ratio about 2.4. It's still pretty strong association. So again, this is kind of using a different metric to show that there's a pretty strong evidence of within subject correlation. So it's kind of really important that you do not ignore this correlation. So we'll try to fit the model we try to fit. We will model the log odds of positive response equals a linear predictor. So like we put time in months in this case as a treatment indicator, and also the interaction between treatment indicator and time. So this mean model is really similar to the previous case, previous example, right? So this is saying that the rate of decline in log odds among the first treatment group, this is this coefficient telling you the difference between treatments at baseline. The beta 3, the interaction, is the difference in the rate of decline between two treatment groups. So this is what we are mostly interested in. And to model the within subject correlation, we add a random intercept here, UI, and assuming the UI come from, Gaussian distribution with some variance. So here are what the results we got from fitting this GLMM. So I think we mentioned that the parameter we are most interested in is the interaction. So this term, so the estimated coefficient is negative 0.137, and it's statistically significant. It's really kind of the reactance is negative, indicating that treatment B actually indicate like a stronger effect, because in this case, like the positive response is like more severe symptoms. So like so negative number means less odds of reporting a positive response, which is actually a good thing. It means treatment B actually have a stronger effect, seems like. And then the sigma is the standard deviation for the random effects. The sigma in this case is estimated to be 4.5, which is pretty strong. So indicating that there seems to be evidence of pretty strong within subject heterogeneity. So to summarize this results, so from the fixed effects estimate, because this effect is significant, and also we wanted to sort of understand what this means. This is really the difference in the rate of change per month, because the unit of time is months. Remember the whole trial is 12 months. So in order to estimate the pre-post difference, we wanted to multiply 12 by this number. That will be the log odds ratio scale, and then we can take exponential to get odds ratio scale. If you actually do the calculation, it shows us the odds ratio comparing 12 months decrease in the risk between oops, I'm sorry, I think keeps I need to go back to the sorry the odds ratio comparing 12 months differences in risk between treatment A and B is actually 0.2. It's a really strong odds ratio, I think. And there appears to be evidence suggesting that there's substantial within subject heterogeneity. Let me see if there's a question. Oh, there's a question asked, would it be possible to access this code as well? Yes, I think following the workshop, I will also send the code and data for this example as well. So let's just so finally so basically that's the end of this example. I think I didn't show a lot of details, but in case some questions asked, I think some of you might ask, if you look at this correlation matrix, right? So it appears that the correlation is not exactly exchangeable because you see a stronger correlations here, like much weaker correlation around here. So why not using a random intercept and random slope? Actually, so for when you are doing binary data, typically binary data is probably the worst examples in the sense that with binary data, the amount of information in the data is much smaller than in the continuous data. So it's actually become more challenging. So in a few different packages, I tried to fit both random intercept and random slope. It seems like the algorithm have trouble converging, meaning we try to find the really maximum likelihood is always try to find the parameter that maximize your likelihood function. So you wanted to find a global maximum, but a lot of times if your model fails to converge, it means it cannot reliably find where the maximum is. So in that case, the results are not that trustworthy. So I think with the current data, with this particular data set, maybe there's not enough information for us to reliably estimate a random intercept and a random slope model. So that's why I'm presenting it here. But I do from that I do wanted to say that when you especially go to binary data, there's additional challenges like computational challenges or model fitting. So typically you see more issues with more complicated data. So that's why for binary data, I generally recommend is using relatively simpler models because that's really not a lot of information to identify all those complex models. So that's why even though we know the correlation structure is not exchangeable, the using the random intercept only is still, it's probably still the best we can do for estimating our targets. So finally, I'll just maybe mention a few differences, like what are the alternative approaches. So in this workshop, I really focused on random effects or mixed effects models. So if you wonder, what are the other options we can do for longitudinal data? So the first one is a so-called naive approach. You pretend the data are independent. Now, I think hopefully I convinced you that that's not acceptable because if you ignore the correlation, typically you will a lot of times you just simply get the wrong conclusions. And even if sometimes you might still get the correct estimates, your standard errors might be wrong, and you're not really using the data efficiently. And the one other model is called the marginal model with GE, which if you attended the previous workshops, we are focused on that. So I'm not going to talk too much on GE today. And then there are also other types of conditional models. Today I think the random effects is saying that assuming there's kind of like underlying observable random effects that is sort of causing the correlation between different physics, right? But there's another type of model, it's called transition models. It's a little bit like, you try to build dependence of the current response based on the past responses. Meaning at the visit J, you try to build a model. One model is called a Markov first order Markov model, which is saying that the current response is only influenced by the most recent visits, right? So for the subject I, your outcome at the visit J, is dependent on the outcome at J-1, the previous time point, right? You can build a response regression model for that, you use the previous history as a covariate in the model. You can also, add additional covariates. This is another type of model, it can be useful in some cases. Yeah, but I think it's not used as widely as mixed effects models. So to give a summary, so in this workshop, I really kind of try to give an overview of the mixed effects models. The first half is more focused on linear mixed effects models on the continuous data. The second half is more like generalized linear mixed effects models on non-Gaussian data, especially discrete data. So overall, generally speaking, so the goal of these models, they are extensions of existing linear regression or generalized linear models to handle correlated data. So the way it works is like they add, random effects to the model, to the predictor part. And then by using the random effects, they induce different type of a correlation structure. And with also these random effects, they can sort of help to explain heterogeneity across individuals to allow like trajectory to differ from individual to individual. And for both model estimation and inference, just to keep in mind that the interpretation generally have subject-specific flavor as opposed to population average effects. And of course, related to that, an added bonus for the random effects model in general is that you are able to reconstruct subject-specific curve. It's like just like as the example I showed you before, for each individual, you can add once you estimate the random effects, now you can reconstruct the curve and then see how that compares to the observed data. And then you can also do prediction, which I did not talk about before, but like, if you have some individuals, right, maybe they have missing data at some time point. Let's see, if your study has visit 1, 2, 3, 4, 5, but for some reason, some individuals, they only have data at 1, 2, 3. So you wanted to predict what the outcome would be if the, provide the response at visit 4 and 5, right? So with the marginal model, you really cannot do that. But with random effects model, you can still include fit a random effects model, predict the random effects for this individual. It may give you like sort of the estimated random intercept, random slope, and then based on the existing 3 visits of data, you can reconstruct a curve. You can give a pretty good prediction of the future outcomes. So other issues, I think those issues we probably have discussed before. So missing data, they handle missing at random with no problem, as opposed to GE. GE really requires a very strong assumption of missing completely at random. And the comparison with marginal models, I think we discussed about this before. And finally, so we in the previous models, including data examples, I always show like so-called parametric models, meaning you kind of assume the trajectory, the shape of the trajectory come from some simple family, let's say linear trajectory family, or a change point family, or even sometimes a quadratic form. You have a family. So, but they are typically still a little bit simple. For some studies, you wanted to have like more flexible, nonlinear type of relationship. So I do not talk about this in both of these workshops, but in the statistical literature, there are something called non-parametric regression, so which can be used in longitudinal setting as well. In those cases, you do not assume the type of shape. It could be any type of nonlinear shape, but you use some sort of a special spline-based model to try to account for that. So hopefully, in the next sequence for the workshop, I think I will talk about more intensive longitudinal data. So hopefully in that workshop, we'll cover a little bit more about the non-parametric models. I think that will be the end of the workshop. So like so I think I will only leave some time to see if there are additional questions. Yeah, I see raised hand. Please feel free to unmute yourself and ask a question.
Yeah, I had two quick questions. So the first one, just so that I could understand, if you could go back to the previous slide, where you talk about missing data. So are you saying that with GLMMs, it's okay to have a certain proportion of data missing? Or yeah, I just couldn't completely understand. Maybe because I missed the previous workshop. If you could explain this missing at random process a little bit.
Yeah, sure. Yeah. So like missing, I think in statistical literature we kind of classify different type of missing. It's like we have a few example different assumptions or examples. The strongest one is called missing completed at random. Just think about, in the longitudinal setting, right? So you basically you have a study, you try to to get a measurement from everybody. Let's see, you try to get a questionnaire, but sometimes people do not respond, or they respond, but the response was like not valid or something. So there could be all sorts of different reasons that are leading to missing this, right? So missing completed at random, that really is really strong, seeing that the mechanism or the probability of missing is totally random. It does not depend on any factor at all. So it's like like at visit 1 and visit 2, the missing could happen to anybody with equal probability. So that's kind of like a missing completely at random. So that's like a really a very strong assumption. And there's another assumption which is a little bit less restrictive. It's called missing at random. That means like the chance of probability of missing depends only on observed data. In the sense that let's give an example. For example, it could be that in a study you have everybody's age, and for some reason you observe that there's a higher chance of missing among older participants, right? Maybe they are more likely to guess because their health conditions are not that great compared to younger people, so it's more likely you get missing data from them. But in that case, as long as if you have their age data, if older people have a higher chance of missing, that's still called missing at random. In this case, GLMM can handle this type of situation perfectly fine. But GE cannot. GE really need to require the missing is like really completed at random. So and then of course in practice there are also cases where missing is not at random, like dropout or something, maybe due to missing due to death, or there could be other reasons. It does not even satisfy missing a random assumption. Yeah, but overall, in terms of missing data, GLM because it's using a likelihood approach, it actually it's at least a little bit better than GE, I think. Yeah. Did that answer your question?
Yeah, kind of. So like, I guess like practically when you're building your data set, if someone's lost to follow up, you wouldn't necessarily include them in your data set for the analysis, right?
Well, actually, it's kind of the handling missing data correctly in longitudinal data. It's actually a pretty complicated topic by itself.
Yeah.
And then like there are some special statistical methods developed to handle different cases. Like it's very common to have dropouts in longitudinal analysis. I think if you just take out those individuals, actually it could cause some bias. So there are some ways. Some are based on imputations, some are based on weighting approaches.
Mhm.
So yeah, so those are, I probably would, if you have, if the missing proportions is small, I wouldn't worry
Mhm.
too much. But if the missing proportion is it's a little bit higher, let's see, higher than 10%, or 20%, I would definitely look into sort of more sophisticated methods.
All right, yeah, thanks. And then I had one more quick question. I'm not sure if it's easy to answer, but I was just wondering if you could help explain how to account for clustering in these models. Yeah, so like I'm dealing with data from a set of different pharmacies, and there could be pharmacy level clustering among individuals. So I was just curious how to address that in your code or analysis.
So like just to clarify, so do you have both clustering and the longitudinal data, or do you just have clustering?
I have both.
Both. Okay. Yeah. So clustering, I mean, as you can see, like this approach of using random effects to account for correlations. In this workshop, I really focused on the longitudinal example. But this principle of this idea, actually, it can handle any type of correlation, right? So correlation due to clustering is sort of another example of, you can use that it can be handled by random effects. So basically, I think so. Like maybe let's see if I can go back to some of the slides before. Let's see how I mouse. Okay, let's maybe go back to linear mixed effects model. Yeah, so this is like a general version of linear mixed effects model, right? So you can, where the fixed effects and the random effects, they are both flexible. You depends on what your interests are. You can add random effects over here, in the sense that now if you have subject specific random effects, right, you are accounting for correlation induced by shared characteristics from individuals, right? If you have suspicion of clustering effect, let's in your case, pharmacy, for example, you could add additional sort of pharmacy specific random effects here. It could be random intercept or random slope or whichever you like. But if you put additional random, they will not vary by I, but maybe vary by, I don't know, maybe you can index that by K or something. K indicated which pharmacy, right? So you have something like UK as additional random effects. If you do that, you'll be able to account for those additional variations. Yeah.
Thank you so much. Yeah, thanks.
You're welcome. Yeah. Any other questions? No. If not, I think that's should conclude our workshop. So Shirley, do you have any final concluding words or anything else you want to say?
Yeah, I'll be sending out an evaluation survey that everyone can fill out, and then the recording will be on the website within 2 weeks, and any other resources that Dr. D would like to share.
Yeah. I would, as I will, I showed 2 data examples. I think I already shared the links for the first one. The second one, I'll also share that with you as well. So if you have any questions in the future, feel free to contact me. Thank you.
Thank you for joining.
Thank you, everyone. Bye.